Chapter 11.5 is the alternating series. Now, when we talk about the alternating series, we are talking about a very particular alternating series. The alternating part means that it switches from positive to negative to positive to negative, and it could start negative, positive, negative, positive. The starting doesn't really matter. So that's the alternating part. But the kind of alternating series we're talking about is the kind where each of these terms, b1, b2, b3, regardless of the -1, the alternating part, is decreasing, but also they're decreasing and reaching 0. So the limit of each of those term b sub n is equal to 0. Those are the kinds of alternating series we are talking about. Let's take a look at what happens when we have such a series. When we have such a series here, b1, so remember each of these terms are decreasing. The absolute value is decreasing. Take a look at what happens when I start grouping them together, something that looks like this. What can you conclude about each of these? Well, it looks like within each parentheses, b1 minus b2 is going to be a positive number because b2 is smaller than b1. Just like b4 is smaller than b3. So this one is also going to be positive. This parentheses is also positive. Each of these groupings will always be positive because of this condition right here. The fact that each term is decreasing, right? So what can we conclude? The number one conclusion, the first conclusion from this kind of series is the fact that we do have some sort of a positive sum. Or we can say that the sum is greater than 0, right? Now, what else can we say? What's kind of cool is that if I take this same series and I group them slightly differently, so instead of grouping the first two, then the second two, then the third two, I'm going to group the second and third one by factoring out the negative. So this is going to be negative b sub 3, right? So then if you take a look, if I distribute in the negative, I'll have minus b sub 2 plus b sub 3. And I'm going to keep doing that. Group the next two together, and then the next two together, etc., etc. Right? Now, if we do that, take a look at what happens here. What do we know about each of these parentheses? Each of these parentheses are also positive, right? Because b sub 3 is smaller than b sub 2, again due to this condition, the fact that each term is decreasing. So this is also, each of these parentheses are positive. Now, what does that mean? That means this first term, b sub 1, is actually the largest possible sum because I'm starting off with b sub 1 and then I'm subtracting positive terms every single time after that. So b sub 1 is going to be my largest possible sum. That's going to be my second conclusion. Now, combining these, take a look at what that means. That means my sum, S, is going to be greater than 0, but less than b sub 1. Right? So my ultimate conclusion is that my sum is positive, it's greater than 0, but also less than b sub 1, which means no matter what kind of a series we have, if an alternating series, as long as it's decreasing and the limit is reaching 0, we have a convergent series. Okay, so for example, let's consider the alternating harmonic series. Now, the alternating harmonic series is just the harmonic series, except it switches from positive to negative, positive, negative, positive, negative. If you notice that each term b sub n is decreasing, we know that. We know that the limit approaches 0. 1 over n, the limit approaches 0. So, but what about the alternating one? Now, again, according to what we just learned, if I group these two together this way, pair them up this way. They're the exact same series. We see that this is positive. Each of these parentheses are positive. Okay, so we have a positive sum. So this is going to be, this sum is going to be positive, right? If we group it a different way, if we group, say, this way, right, and I factor out the negative, right, do you see how this 1/2 minus 1/3 is also positive, 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 positive? So I am going to be subtracting a positive number from 1 every single time. So that also means, in this case, that this alternating series, alternating harmonic series, is definitely going to be less than 1, the first term. What does that mean? That means the sum actually does converge to a value between 0 and 1. So the alternating harmonic series is convergent. So the thing is, we actually do not have to show all of this work all the time. Not anymore, because what we know now is that any series, what we're saying is that any series where each term is decreasing, right, as long as 1 sub n, so 1 sub n plus 1, each term is smaller than the previous term, okay, and as long as the limit of each of those terms reaches 0, then the series is convergent. Then the alternating series is convergent. And this is what we call the alternating series test. Right? So as long as we have any alternating series where each term is decreasing and it's decreasing to 0, we have a convergent series. So let's take a look at the next one. In this case, we know that it's alternating. Awesome. Do we know that we need to satisfy 2 conditions? The second condition is that the limit goes to 0. So that one's a little bit easier. Let's try that one. If you take a look, we're going to L'Hopital's rule it. So you can say the limit, I mean, you don't really have to, but the limit as n approaches infinity of 2n over 3n squared is equal to the limit of 2 over 6n, right? So this equals to 0. The limit, and we have to prove that every single term b sub n plus 1 is less than b sub n. Now how do we prove that? Well, if we're actually asked to prove it, what tells you that this is constantly decreasing? That's what I want to know in this case, that this is always decreasing. That word should trigger something, and that is slope. So if I take n squared over n cubed plus 1 and call it some function, if I find the slope and prove that it's always going to be decreasing, it's always going to be negative as n increases, then we have a surefire proof that each term is decreasing. Now be careful when you do the derivative. We are not using L'Hopital's rule. How do we find the derivative of this? You actually have to use the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Right? So let's push this aside. What does that give me? Well, in this case, I have 2n to the 4th plus 2n minus 3n to the 4th. The bottom is always going to be positive. So let's take a look at the numerator here. This looks like I have a negative 3n to the 4th plus 2n over n cubed plus 1 squared. Now this means taking a look at this, this shows that in this case, whenever n increases, as n increases, right, this limit will always be negative. Right? As n increases, this will always be a negative value, which means each term is definitely decreasing. Therefore, this is convergent. This series is convergent. Okay. So next example, this series is also alternating. Awesome. There's two conditions that we have to meet. We have to see that this is constantly decreasing for every term. But if you take a look, I like looking at this one first. Let's take a look at the limit. Does it decrease to 0? What ends up happening here, the limit of this b sub n is just 3/4, which means it doesn't actually decrease to 0. But so it fails the alternating series test. The alternating series test is inconclusive. But that doesn't necessarily make this divergent. What makes this series divergent, it is divergent, is not because it fails the alternating series test, it is because it passes the divergence test. It's the divergence test where I take the limit as n approaches infinity of the full thing, right? It does not equal to 0. Therefore, this series is divergent. Okay? So really, if it fails this portion of the alternating series test, then it definitely is divergent because of the divergence test. And what's nice about the alternating series is that because, for example, the proof that we did earlier, we actually can limit the boundaries. Where'd it go? We can limit the boundaries of our actual sum. We know that it's positive and we know that it's smaller than b sub 1, but we can actually narrow it down even further. So that's what we'll be learning in class on Monday.